Giddy up, freshies. You know what time it is. It's radical time. Let's take a look at what we got here. Look at number 1 and 2. And you're going to see some similarities. Well, do you know how to do the first one? I mean, that's just getting like terms together, right? Get your 3x, you take away an x, you add 7x over there. Well, how about this next one here? You get 3 of those root 2's. You take away 1 of those root 2's. Then you add 7 of those root 2's. And let's do the first one. If I had 3x, take away 1x, puts me at 2x. 2x plus 5x, or 7x. That leaves us at 9x. Let's look at this next example. If I had 3 of these root 2's, I take away 1 of them, and I add 7 more, same thing. Now I've got 9 of those root 2's. Now let's go back to the first one here. If I had plus 2y, and I take away 6 of them, what's that leave us at? Negative 4y? I believe so. Negative 4y. Let's do the same thing for our root 3's here. I got a positive root 3. Take away 6 of those root 3's. Puts me at a negative 4 root 3. And then this p term right here. You know, just like this root 5 here. There are no like terms for it, so I can't combine it with anything else. So that's how you add radicals. You basically need to simplify under the square root until the number inside, which is called the radicand, until that number cannot be broken down any further. In other words, there cannot be any perfect squares that go into that number. Alright. Now multiplication. Well, if you know how to multiply numbers, you know how to do this. Okay, there's just a very simple operation here. Now, remember when you're multiplying numbers together, let me ask you this. Is 4 times 3 the same thing as 3 times 4? Well, the answer is yes, because when you're multiplying numbers together, it doesn't matter which order you put them in. Okay, that's the commutative property of multiplication. Likewise, I can look at this right here and rearrange it. Now I can do this in my head, but for now, let's do it like this. At 3, at 2, there's an imaginary 1 right there and an imaginary 1 right there. Let's see what else we got here. Got a 7 right there and a 6 right there. You notice these are all on the outside of the radicals, okay? Which means I can bring them up front. I can have 3 times 2 times 2 times 7 times 6. See how I just brought all those numbers out to the front? Okay. And then remember that other property of radicals says if I've got numbers under the square root sign, the radical symbol, and I want to bring those together, I can just combine them underneath my square root. So, what do I got? Well, I got this 2, 3, 2, 5, 2, and a 3. Now those are all under the square root, so I can just multiply those together. So I've got my radical sign right here. And then I have that 2 times 3 times 2 times 5, 2 times 3. So, good way to think about it. That number is either on the outside of the radical or it's inside the radical. If it's on the outside and we're multiplying, and this is just a string of multiplication, I can always multiply the numbers that are on the outside. The numbers that are on the inside, they're kind of stuck in there. Okay? They're all stuck in there, but we're going to multiply them together and see if I can take a perfect square out in a moment. So what is 3 times 2 times 7 times 6? So that comes to 252. So that's on the outside. So we get 252. Then I've got the square root of 2 times 3 times 2. So what is it? 2 times 3 times 2 times 5 times 2 times 3. Oh, I don't know, I think it's 360 though, from what I recall. Let's pretend it's 360 if it's not. And then, what I'm looking at is the number under the radical. I'm asking myself, are there any perfect squares that go in there? And the answer is yes, 36. So, which means we can rewrite this as 252, shown on the outside, and I can break up that 360 into the product of two numbers. It's going to be 36 times 10. Now I chose 36 because 36 is a nice, clean, perfect square. So this all becomes 252 times 6. Now a lot of people are going to put root 6 there. But the square root of 36 is not the square root of 6, it's just a plain old 6, right? I mean, the square root of 36 says, tell me what number, when I square it, gets me a 36. So that number is 6. On the outside now, it came out. And then the root 10 is stuck inside since there are no perfect squares in there. So I got to figure out what 252 times 6 is since those two numbers on the outside. And then I'm left with 1512 root 10 is my final answer. Alright. Let's take a look at 4 here. So one of the properties of radicals says that I can break up anything that's under a square root symbol into individual products. So I can break this up under root 20 there. Now once you start getting good at these, you don't need to do this step. This is like the baby step right here. But it's good to kind of see how it works when you're first learning this. Square root of 20, well, I think we know how to do that by now. I can break that up into square root of 4 times the square root of 5. Square root of x cubed. Okay, what does that mean? Well, that's really square root of x times x times x. Now remember, when we're taking a square root, we're taking a square root, which means we're trying to find groups of 2 that we can take out. So I got a group of 2 there. Now you noticed I have one x remaining inside the radical. Okay, so he's kind of stuck in there. But these guys, since they were a group of 2, I'm able to take those out now. Because we know that the square root of x squared is just x. And that's what we have here. The square root of x squared. So an x is going to come out there. And then you have this guy stuck inside. Okay. Now look at this y to the 5th here, the square root of y to the 5th. How many groups of 2 can I take out? In other words, what you're asking yourself is, how many times does 2 go into 5? Well, 2 goes into 5 2 times. And how many do I have left over? Just 1. Then I go to the p to the 4th here, square root of p to the 4th. How many groups of 2 can I take out of that? Well, p squared, right? Is there anything left over? Nope, they all came out. Because I really had p times p times p times p, and I was able to take one group out, 2 groups out. So that's where this 2 came from. I took 2 groups of 2 out. Alright, and then clean this up a little bit. So I know what the square root of 4 is. That's just a 2. So I'm done with that. Then I get everything on the outside together. So I have an x on the outside that came from right here. I have a y squared on the outside. I have a p squared on the outside. Since these are on the outside, I can bring them all together. So I'm done with that, done with that, done with that. What do I got left? Well, it's all the stuff that's under the square root. Remember, I can combine these now since they're all under the same square root. So I got 5 times x times y. This gets me 5 xy. And since I can no longer simplify this, we are done. Now remember, you guys can always pause this. I mean, it's a video, so always pause, rewind, watch it again if you need to. But I'm kind of going fast here. So 2 ways you can do this. You can simplify this first one here, and then simplify this next one here and combine them. Or if you want, since it's a radical multiplied by another radical, we can make one big square root sign and put all the numbers underneath it. Might be easier. So let's do, so we're going to have to do 32 times 6. What does that come to? 32 times 6 is 192. Now remember, this is all under, we're making a big square root now. So 192. How about my g terms? Well, I got g to the 7th times g to the 3rd. That comes to g to the 10th. T to the 17th. That's the only t I got. Then I've got, what else do I got? Z to the 5th. And w squared. Okay. So here's where I could break it down into square root of 192 and a square root of g to the 10th. Okay, I could do that, but to save time, I'm not going to. So the question is, are there any perfect squares that go into 192? I think, yeah, 64 goes into it. Square root of 192 is really square root of 64 times the square root of 3, which is just 8 root 3. So I'm going to do that in one step here, so that's just 8 root 3. Okay. How about the square root of g to the 10th here? Well, how many g's can I, how many groups of 2 can I take out? Well, 5. Any stragglers left inside? Nope, I got them all out. Let's go on to t now. How many groups of 2 can I take out of 17? Well, I can take 8 groups out, right? So, taking 8 groups out. And then is there anything left over? Any stragglers? Yeah, there's that one left over, that 17th t that's stuck inside. Same thing with the z's. I can take 2 groups out. And I got 1 stuck inside. And for the w's, the square root of w squared is just a plain old w, which is on the outside. So now, I multiply all the stuff on the outside together. That's on the outside, those 2 are on the outside, he's on the outside. And then I get 8 g to the 5th, t to the 8th, z squared. Oh, and I also got this w over here. I forgot about him. And what's left on the inside? Well, remember, I can multiply everything that's under the square root. So 3 times a t times a z is just going to be 3t z. And we are all done because nothing can simplify in here. I can't find a perfect square in 3, and I can't take anything out of t and z. Okay. So this is kind of like our first problem, but the only thing is, the first thing we got to do is break it down as much as we can. So I'm going to do some of this, do some mental math here. So this is really, well, what's the square root of 20? Square root of 20 is the square root of 4 times the square root of 5. Square root of 4 is 2. So 2 times 5 is 10. And then I have a root 5, right? Square root of 20, square root of 4, times square root of 5, so that's just 2 root 5. 2 times that 5 was 10. Okay? Plus 3 root 8. So this is going to be 3, so what's the square root of 8? The square root of 8 is just square root of 4 times the square root of 2, which is 2 root 2. So 3 times this 2 on the outside is going to be 6. And I get 6 root 2. Square root of 45. Square root of 45, what's that? Well, that's going to be the square root of 9 times the square root of 5, which is going to be 3 root 5. So if I take this 2 on the outside and multiply it by this 3, that gets me 6, and then root 5. Minus 7 root 2, I can't simplify that. So at this stage, we're looking for like terms. Remember, like terms have the same variable raised to the same degree, or if we're dealing with radicals, in this case, the same, when they got the same radicand, basically, the number under the radical. So this is a root 5 term, that's a root 5 term. I've got 10 of these things, plus 6 more of those same things, so that puts me at 16 of those things, or 16 of those root 5s, done with that, done with that. Then if I had 6 of these root 2s, and I took away 7, puts me in the negatives, -1 root 2, and I'm all done. Now of course you can't combine these to make 15 root whatever, because these are not the same, root 5 and root 2. Alright, So this says take 2 times this giant quantity here. So let's just start breaking it down. Order of operations, we'll go inside the parentheses first. So what is the square root of 18? The square root of 18 is just 3 root 2. So this is going to be times 3 root 2xy plus 4 root 2xy. 5 times 3 is 15, so I get 2 times 15 root 2xy plus 4 times root 2xy. Now let me ask you this. What we got in the parentheses here, are these like terms? I got 15 of these things, these root 2xy's, and I got 4 more of those root 2xy's. Now you might not think so, but since they are identical, we can add them together. Okay, so I've got 15 of these things plus 4 more of those same things, puts me at 19 of those things. So I've got 2 times 19 root 2xy. And then I just distribute the 2. So it's going to be 38 root 2xy. Now you might be asking yourself, why didn't I distribute the 2 inside here? Remember, you're either on the outside or on the inside. You can't go back and forth, okay? Unless you're coming out, as in a perfect square. But no, you don't distribute this 2 on the outside into the inside there. Okay, some basic properties here. We kind of already been going over this. So if I had like a number here that had factors, so like 20, that could break down to individual factors, just like you see here. When I'm dividing numbers, I can break a giant radical that's got a fraction inside into 2 separate radicals, one in the numerator, one in the denominator. Okay, so here's an example right here. And basically we're going backwards from the first example. I can start with individual factors, and if I needed to, I can always go back into, after I multiply those factors together, I can do that. And obviously the division one works the other way too. If I got a square root over a square root, I can make one giant square root. So rationalizing radicals. Basically all that means is we don't want any radicals in the denominator. So no radicals on the bottom. So this one is no good, and this one's no good, this one's no good, okay? We don't like having radicals in the denominator. Don't ask me why. Probably some geezer having a bad day. Some mathematician said no more radicals in the bottom. So we abide. What can we do? Let's take a look at number 1 here. So, would you agree, as an aside, that the square root of 5 divided by the square root of 5 is 1? Well, yeah, anything divided by itself is 1. Okay. And so what we're going to do is, additionally, what is the square root of 5 times the square root of 5? Well, that's what? Root 25 if we apply our what we know about radicals there, which is just a plain old 5. So it turns out anytime you got something under radical times itself, you always get that radicand out. Okay? So it's kind of like a little something handy to know. So what we do then, we just multiply top and bottom by whatever that radical is in the denominator. Because, what did we really do? Well, we really just multiplied by 1, right? Root 5 over root 5, so we didn't change anything. But look what happens. On the top, remember, multiplying fractions, you just multiply straight across. You get 3 root 5. On the bottom, we just said root 5 times root 5 is just a straight up 5. No more radicals in the denominator, so we're happy there. And then all thing we got to check is, does this reduce at all? The stuff on the outside? Answer is no, so we are done. Same kind of thing here. Got to multiply top and bottom by that radical in the denominator. So 3 and 3. 2 times root 3 is just 2 root 3. Root 3 times root 3, you just get that thing out, and we are done. Remember, if I've got a fraction under a square root sign, I can break that up if I so desired to get root 3 over root 7. Don't like radicals in the denominator. Multiply bottom by root 7. Multiply top by root 7. Now look here. A root 3 times a root 7, what is that? Well, they're both under the radical. So I can multiply those together, keeping them under the radical sign, which is root 21. And then, of course, root 7 times root 7 we said was just 7. Root 21 cannot be broken down any further, so we are all done. Let's looky here. Root 6 over root 4. Now, you might say, well, let's multiply the top and bottom by root 4, which you could. It would work out fine. But we do know what the square root of 4 is, so why not just simplify right now? And maybe save ourselves some work. Root 6 I can't do anything with, but the square root of 4 is just a 2. So that would be it then. All done. So looky here. Okay. Well, got to get rid of that root 20 down there. So we could, well, we could simplify it first. Well, what is the square root of 20? That's just going to be, what, 2 root 5? Okay, so we could just do that. Or we could multiply top and bottom by root 20. It really doesn't matter. So let's just simplify it first. 10 all over. Well, we said root 20 was 2 root 5. So 3 times 2 root 5 is going to be 6 root 5. We don't like having radicals in the bottom, so we're going to multiply top and bottom by root 5. Notice I didn't multiply by 6 root 5, only what the radical was down here. This 6 is fine, all by himself. Okay. So what do we get then? This is going to be 10 root 5 all over. Well, this is going to be 6 times, what does all this become down here? Root 5 times root 5 is 5. So 6 times 5 is 30. And then I got to see if this reduces at all. Does 10 over 30 reduce? Yeah, that reduces to 1/3. So this is going to equal 1 root 5, or just root 5, all over 3. And that is all. Let's look here. Okay, so I'm always looking to simplify before I do anything. I see the square root of x squared, and I know that's just a straight up x. So I might just rewrite this. So I get 3y cubed all over 2x root y. Don't like that root y, so I multiply top and bottom by square root of y, square root of y. And then we got 3y cubed root y all over 2x, and we know that root y times root y is just going to be a straight up y on the outside. And then I'm looking to see if I can reduce anything. Can I reduce anything on the outside there? It looks like I've got 3 y's on top and 2 y's on the bottom, so I can cancel one of those out. So this is going to equal 3y squared root y all over 2x. And last of the examples, same thing here. Don't like getting that radical in the bottom. I multiply the bottom by root 2, multiply the top by root 2, then I'm getting 3 root 2 on top, and then I get 10 times, well, what is root 2 times root 2? That's just a 2, so 10 times 2 is going to be 20, and I can't simplify that anymore. So let's look at the competition you guys had from a couple weeks ago. I think you're going to find this is extremely easy now. So a good strategy for taking a radical test like this is to look through it and see what is the biggest number you're going to have to try to break down. So it looks like 288. Okay. Then what you do is you start making out your perfect squares. 1 squared, and 2 squared, and 3 squared, and 4 squared. And you keep going up. I mean, you probably got most of these memorized, probably up to 12. Okay. But then you said that the biggest number we got is 288. So I'm going to go all the way up to 17 squared, because that's 289. Okay. And then, you know, the rest of these you really don't need after that, you know, for this particular test. Okay. So, square root of 150. We know it breaks down into 2 radicals. First thing we check for is 150 a perfect square. It is not. So that's when we look to break it up. And it looks like the biggest perfect square that goes into that is going to be 25. So 25 times 6. And square root of 25 is just a 5. So 5 root 6. So I'm going to fly through this because this should be pretty easy by now. Is square root of 56 a perfect square? It is not. So what is the biggest number that goes into it? The biggest perfect square is 4. So 4 times what? 14. I know the square root of 4 is 2. 2 is now on the outside. 6 times 2 is 12. Final answer, 12 root 14. A couple ways you can do this. You could break down root 20, break down root 20. But they're like terms right now, so why not just combine them? I got 3 of these things minus 1 of those things. So I just got 2 of the things. Now I can break it down. Root 20 is root 4 and root 5. Root 4 is 2. So 2 times 2 is 4. Final answer, 4 root 5. Alright. Square root of 50. Is that a perfect square? No. What's the biggest perfect square that goes into it? 25. 25 times what? 2. 288. Is that a perfect square? No. So when I'm trying to figure out what's the biggest perfect square, I basically just cut it in half to figure it out. So that's what I did. I tried 144. Turns out 144 is a perfect square. And 144 times 2, 72 breaks down into 36 and 2. So that's a nice clean 5, that's a nice clean 12, that's a nice clean 6. And now, notice we have all like terms. Root 2, root 2, root 2. 5 plus 6, take away, or 5 plus 12, take away 6, put us at 11. Alright, freshies. Ball's in your court. Godspeed.